Okay, so I'll try to do an explanation of a little anatomy of Lisp because that's very helpful in figuring out what Lisp does. So we'll have two parts. One, I'll try to explain to you, first of all, this whole issue of const cells and how lists actually are represented, at least conceptually, in the memory. And the second part that we want to talk about is how the evaluator works. What does it do actually, so that you're no longer surprised at the quoting and unquoting, etc. And then this is like the anatomy lecture of the Lisp, and then we'll get back later on to talking about specific things such as the project code in a different one. Okay, and since I'm just copying this for the first time, rather recording this for the first time, I'm not quite sure how it's going to work, so we'll see how this works. Anyway, so look at the console picture here. So first let's start with what is an atom in Lisp. So an atom in Lisp essentially is a sort of a structure in a memory where you have the print name of the atom, a value of the atom, and a separate thing called the function value of the atom, and then a third thing called the property list for that atom. Now the interesting thing is that unlike in scheme where a value, a symbol can only have either a normal value or a function value, just one value. In common Lisp, actually you wind up having two different values. The value of the symbol itself as well as the function value. To see that this makes sense, notice this, okay? So for example, let me say, that let's do this, set q my fun equal to 3. So now my fun has the value 3, and then I also do defun my fun xy plus xy. Okay, so now notice that I have two different values for my fun. So depending on how it gets evaluated, if it's evaluated for its function value, it will act as a function. If not, it will act as its value. So for example, if I say my fun, I do get 3. And if I say my fun 3 and 4, I'll get 7. Okay, the reason this makes sense, I'm not asking you to actually ever have a symbol which represents both a function and a value, but you need to understand how common Lisp works, and so it does have these two different slots. Okay, now the way you get so for example, if you want to get the functional value of my fun, then there is a way of doing that. So for example, if you want to set j to be the value of my fun, you just do value of my fun. Okay, so now j is 3. If on the other hand you want to set j to be the functional value of my fun, there is this sharp quote macro. There's this sharp quote macro, this right here, and if you do that, then j will now be set to the closure function. Notice that my function is a closure, so functions are represented as the closures in common Lisp. So in essence, j now remembers, j now is pointing to the functional value of my fun. Now we'll see in a little later that now j actually can be used to reach that functional value. So if you say fun call, which is a way of calling functions, j on numbers 5 and 6, you should get 11. Okay, so that's basically to just show that an atom really has both a value and a function value. It also has something called a property list, and we'll talk about that later as needed. The other thing is, how do lists behave? So really lists are made up of what are called const cells. A const cell, you can think of it as like basically a domino, two domino pieces joined together. Okay, so and then you can put a pointer from here and you can put a pointer from there. Okay, so for example, if I just have a list with one element a, then that's really nothing but a pointer to this const cell here, where this const cell really has the first pointer is pointing to the symbol a in the memory, which is basically could be this atom here, and then the second is pointing, is showing that is the end of the list, so it's like pointing to a null pointer. So we'll just put an earthing, conceptually we'll put an earthing here. So similarly, if I now have a list with an element B, so that's basically a separate console. So when, let's say I say P equal to list A, then set Q P equal to list A, then P is now pointing to this whole console. And similarly, Q equal to and set Q list B, then Q would be pointing to this console here, where then the first cell of this console is pointing to B and second cell ends in the earth. Okay, now when I essentially append these two lists together, essentially what I'm doing is I'm taking this pointer here and pointing it to here. That's it. Okay, so appending the two lists above will get me a new list which has two consoles, where the first console's second part is just showing to the second console. Okay, and then when you do car and coulda, really what you're doing is car basically gives you the pointer in the first cell of the console, and coulda is just giving the pointer of the second cell. That's all it's doing. Okay, now in this case, coulda of the second cell will just give you nil, because there is second cell is best pointing to null. Okay, whereas if I do coulda of this cell, so I have a pointer to this whole list here, right here, and then car of it would be the pointer A, and coulda of it is basically this pointer. Now this pointer happens to be essentially the list B. Okay, so that sort of removes the surprise about what's going on. And by the way, car and coulda are really also used as first and rest in Lisp. If you are interested, the reason it's called car and coulda is in the old days when there was this IBM 794, I think is a computer, it used to have a large byte size, and then the first part would be called the car and the second part would be called the coulda. Anyway, so that's your appending. Now one interesting part is as long as I have a console, you might wonder, why can't I have pointers from the both cells to be to symbols, right? I can do that. So for example, I can say a dot cell essentially would essentially take put a pointer to A and a pointer to B. Okay, so in that case, essentially if I do car A, I'll just car of this list, I'll get A, coulda of this list, I get B. Okay, so to see this, look at this. If I to get a dot product, I'll say set Q dot cell to be cons of A and B. So I get A dot B. Now car of dot cell is A, coulda of dot cell is B. Notice that normally you tend to think coulda is always a list. That's not true. Coulda is just the pointer to the second part of the console. And if that's actually pointing also to a list, so be it. Okay, so now you can also say interesting things like suppose I do so normal cell would be set Q normal cell cons of A to list B. That would be AB. Okay, now if I do car of normal cell, I get A, and I get coulda of normal cell, I get B. Okay, by the way, as long as I'm here, there are some special commands at the interaction at the Lisp cell that you should know. Star will always give me the last thing that is returned. So suppose you just ran a very time consuming function and you forgot to remember the value returned by that function in some variable. Don't worry. So in fact, if you want to, for example, remember this value in some function, I can always do it by just saying set Q last result and just say star. So star will always be bound to the very last thing that is returned. And similarly, star star is bound to the second to last thing, and star 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 is bound to the third to last thing that is returned. Okay, so that's just a useful thing to remember. Okay, so that's about the cons cells, and you should be able to play with this understanding to get a feel for what actually happens when you are combining lists. One other thing about these cells is destructive versus non-destructive operations. So the idea is that in general, if you, for example, do destructive operations, what that means, non-destructive operations, what they mean is they copy the const cells that you provide them before doing the operation you want to do on them. Whereas destructive ones essentially just take the const cells and modify the pointers. The problem with destructive ones, the advantage of the destructive ones is that they're actually space saving because they're not generating new const cells all over the memory. But the disadvantage is that you can get into trouble because something that you are pointing to has actually been modified by somebody else later on, and so suddenly your result gets modified. To understand this, look at this here. Okay, nconc is actually a destructive operation. So let's do this. Set q first list is ABC. Okay, and then set q second list is 1 2 3. Okay, now set q my result to be nconc first list second list. It looks like ABC 1 2 3, right? Fine. Now suppose you went and set queued SL to be, so basically what you did was you changed the SL pointer by actually adding an extra value to it. Okay, so let's say set QSL to be nconc SL followed by new. So now SL is now pointing to 1 2 3 new. Now the way you conceptually think now is that you just changed SL, result should still be same, right? If you look at result, notice that result also has a new in it. Why? Because the way the operation occurred when you combine these two destructively is that you took the last pointer from the last const cell of this and pointed it to this. Okay, and then when you did nconc on SL, essentially what you wound up doing is you kept the pointer, and for the last cell here, instead of it being earth, it just now is pointing to new. So what happened now is everybody who was pointing to SL are now affected, and since nconc previously was pointing to SL, now it's now suddenly instead of 1 2 3 has 1 2 3 new. So you should be careful about destructive operations because your intuitive way as to how the program is working would not necessarily square with the way the actual program is working. So when in doubt, at least in the beginning stages, when in doubt, if you are thinking that there is a funny thing happening somewhere, you can always generate an entire list, copy an entire list. Okay, and that would take care of these problems. So there is this function called copy list. So if you say set q SSL copy list SL. Okay, so now SSL is actually a copied version of SL. Okay, so if I say SSL is 1 2 3 new. Now even if I change SL, so if I say set q SL to be nconc of SL and another new thing. So SL now has one more new thing, but SSL hopefully won't have that because it's been copied. Okay, so many operations in Lisp, are non-destructive and many are destructive. And when possible, try to use non-destructive operations in the beginning stages. If you are smart and if you are a master programmer in Lisp, you can use destructive operators, thereby saving space a lot. Okay, so that's about destructive versus non-destructive operators. Okay, now the last thing I want to tell you today is how the programs are evaluated in Lisp. And for that, you should look at this evaluator picture here. So this is also available from the class page, evaluator.jpg. Okay, so here is basically the way the evaluator works. In a Lisp, when you're sitting in front of the evaluator, everything, evaluator is trying to evaluate anything you throw at it. Okay, so if I give it an S expression, an S expression can be either a list or an atom. Okay, so S expression is a list or an atom. Okay, and so if I give an S expression at the evaluator, and that happens to be an atom, the first thing it tries to see is if that atom has a value. Okay, so if it has an atom has a value here, then it will just give you the value back. So for example, SSL is an atom and it has a value because I set the value to be 1, 2, 3, to the pointer to this list 1, 2, 3 new. So when I say SSL, I'll get 1, 2, 3 new. Whereas if I say TYR, then I will get a failure, because essentially TYR, there is a symbol called TYR which is basically undefined as of now because it has no value. Okay, so in that case it will just give you a value. It will just give you an error. Okay, so that's about that. Okay, so that's the first part. If the S expression is an atom, then if its value cell has a pointer, return the pointer. If not, then give an unbound variable error. Now, what happens if the S expression is not an atom? If the S expression is not an atom, then it really is a normal S expression. That means it's a list of things. And then, so the first question is the car of the S expression a valid function? That's what you need to check. Okay, so for example, if I give Scudder SSL, then what it's basically doing is that it's taking the first of this S expression, which is CDR. CDR is a symbol which has a function value. CDR is a symbol which has a function value. Okay, so evaluator then basically takes that function and applies it to the evaluation of SSL. In fact, the way the evaluator works is first it takes the arguments, evaluates all of them, and then passes their values to the function value of the first element. Okay, so if the car of S expression is a valid function, then evaluate the elements of the CDR of the S expression and pass the values to the function, and then return what the function returns. That's what you do. Okay, now there are certain, normally evaluator evaluates everything it sees, right? Except there are special forms which will stop the evaluation. One special form is quote function. So any function which does not evaluate its arguments is called a special form. Okay, so quote is one such function. Quote KQP will just give you KQP back because it essentially doesn't evaluate. Okay, and a shorthand notation for quote KQP is just the KQ, putting quote KQP. By the way this quote actually, so in fact Lisp, when you write quote KQP at the reader, then Lisp evaluator really gets this, a function called quote KQP, and this is done by changing the what's called reader macros, and that's a sort of an advanced topic. In Lisp, in fact, you can change the complete syntax, because when it reads a character such as a quote, then it can actually, instead of reading that in, it can read the parentheses begin quote and then read the next and then put that there and then end the bracket. Okay, and which is then sent to the evaluator. Okay, so that's about the normal functions. Okay, one of the interesting things, of course, is sometimes in fact you would think that the only way the functional forms are evaluated is the first thing is a valid function, and one way something can be a valid function is it's an atom and it has a function value. Another way it's a valid function is that essentially it's a lambda expression. So here is an interesting thing. A lambda expression is just a nameless function, lambda xy, okay, rather lambda x, let's say, and all you do is you want to return plus x and 1. So this is a nameless function which takes value x and adds 1 to it and returns it, right? And if I then put 8 here, this will actually just return me 9. And the reason this works is evaluator sees the car of this whole list, and the car of this whole list is a lambda expression. The car of this whole list is a lambda expression. Okay, and so then it's a function essentially. It's a nameless function, and then it evaluates the arguments. In this case, 8. You know, all these numbers like 8 are symbols which have also as their value the number 8. Okay, so then it evaluates 8, gets the number 8, and then it sends it to this lambda expression, which is a function, and then it evaluates x plus 1, and then it returns 9. Okay, so then basically the extracting the valued functions, if it's an atom, then you look for the function value slot of the atom. If it is a lambda form, so basically the function value slots basically store function closures or the lambda forms. A function really is a lambda form. If not, if CarX is a function, fun call or apply or a lambda function, then you essentially do again act like their functions. Okay. Now there are special kinds of function called fun call, which essentially can be used to apply a named function to certain arguments. So for example, fun call, I can say car on the list 1, 2, 3. Okay, and I'll get 1. I can even do set q j equal to car. Okay, now fun call j 1, 2, 3, 1. Okay, so fun call basically takes the value of j and then looks for the function cell of that essentially. Okay, so we will stop here for today. You should have an idea essentially of how fun call works, how the evaluation works in Lisp. Okay, and how the lists are stored in Lisp. Okay, one other function like fun call is apply, and apply also takes the value of, it basically takes a function and then applies it to the CDR. So basically applies it to the rest of the things. So for example, I can do fun call, I think, let me see, fun call plus 1, 2, 3, 1, 2 rather. Okay, fun call plus 1, 2, I'll get 3 because plus is just added between 1 and 2. Okay, so we'll stop here for now, and then in fact this will also give me a chance to see if this recording is working, and then if it's working I will put up more things like this later on. Okay.